Welcome everyone. We will be kicking off SolidityATL's Web3 Security Session 7. In this session, we're going to go over a few things. We're going to cover Oracle manipulation attacks, front-running attacks, signature malleability, and denial of service related attacks. This whole module and session is going to be focused on specifically diving deeper into these different types of attacks. Starting in the first module, we're going to run through Oracle manipulation attacks. We're going to do a high-level overview, show a simple code snippet, and then do a short hack walkthrough, and then talk about some code smells that you can look for when attempting to detect vulnerabilities in oracles or in smart contracts that could potentially lead to an Oracle manipulation-like attack. An Oracle manipulation attack is when you can manipulate an Oracle implementation to exploit a smart contract. Most of these attacks incorporate some type of flash loan. The reason for this is because when you can increase the supply of a token or increase the supply of a liquidity pool, this can cause varying prices for that token. So this can also do this in such a short amount of time, and which results in oracles maybe not being able to update in the time possible so that it can actually show the real price of a specific asset. So, as we said, flash loans are loans that are lent and paid in the same transaction. I believe we had covered this before, but if you do not know what a flash loan is, this is what they are. Essentially, before the transaction has ended, you essentially pay for that flash loan before that transaction ends. So how this typically works is a user may take out a flash loan, and then once they are supplied tokens, they may perform some type of arbitrage strategy, and then they're able to pay off this flash loan all before the transaction ends. So this is what it looks like. I know it's a little bit blurry, but essentially, an adversary manipulates the source code or the source of Oracle data to create a profitable arbitrage opportunity. Next, this has artificially manipulates the information posted on chain. And then, as we see, this smart contract down here is picking up the artificially manipulated chain link Oracle, and then the attacker profits by exploiting this contract because it has the wrong data. It's picking up the wrong data from those Oracle data feeds. So that's essentially how an Oracle manipulation attack works. Okay, so while there are, I guess technically no simple examples, we're going to show a short code snippet of what a vulnerable piece of code may look like, or what you may see on your end when you're auditing a protocol and you see something interesting that can point to a Oracle manipulation attack. So in this example, due to the spot price use, an attacker can manipulate the price in a single transaction. Using the spot price of an asset is typically discouraged when having some type of liquidity pools or having something where you have to read the oracle of some other token or some other asset. The reason for this is because spot price takes the price of a token at a specific point in time, hence the word spot. But a time-weighted average price oracle, which is a TWAP oracle, typically has a time-weighted average. So it may change depending on a certain amount of intervals that this price has reached. And as we can see, if you were to use a spot price, this could definitely be susceptible to an Oracle manipulation attack because the price of a token would drastically change at a single point in time, or it just may not be updated appropriately at a single point in time. So this is a piece of code snippet that you can take a look at that shows what it looks like when a spot price is being grabbed. This is some older code, but this is just something to kind of store in your brain right at the moment to understand if they're using some type of spot price. All right, so we're going to take a look at a real world hack, Rodeo Finance Oracle Manipulation Attack. And this is all can be seen on the DeFi Hack Labs, which we have shared with you all. So just to go ahead and call out, the root cause of Rodeo Finance was using an improper oracle, and it resulted in an attacker exploiting their protocol. So essentially, we're not going to go through each line of code here, but we're going to cover the high level pieces. So this is a great overview of the root cause. Even though it used a time-weighted average price oracle, the price was calculated by averaging the last 4 instances of the updated price, where each update occurs every 45 minutes. And this could potentially cause issues. One of these issues could be because it's only the last 4 instances used in that calculated average, and an attacker can artificially create those last 4 instances. And also, there are differences in how long this interval should be, but this is one of the issues of why there was an attack. Again, the swap price was manipulated via multi-block sandwich attacks. And then Rodeo Farms utilized the faulty price oracle for LP pricing. And I believe it was a Camelot oracle. But let's go down to the exploit. So this is the exploit. The attacker began with a specific amount of UNS ETH. The attacker manipulated the price through multiple transactions. That's probably where they artificially created those 4 different intervals. We'll take a short look at this. Yep, looks like 3 different transactions. So let's look at the logs. Okay. So they manipulated the price oracle, and then there was also a vulnerability in the health factor check for the price oracle manipulation attack. So essentially, the attacker was able to bypass this when they manipulated the oracle. And so they performed their swaps. Then made a swap on the Camelot router. This is the router that I believe was faulty. So this showed an incorrect price. And then they performed their swap on Uniswap, which allowed them to gain a huge arbitrage in those not those Camelot tokens, but on the Rodeo Finance tokens. So attacker walked away with much more after this price oracle manipulation. And you can run this and watch the state logs and the call stack trace, and kind of dig deeper into what was being changed and how it was changed. But ultimately, you can see that it used an average of the 4 last instances, and then the health factor check for the price oracle manipulation was failed. So these are bypassed, and it's caused the attacker to exploit this protocol. All right, so lastly, let's round it off with oracle manipulation code smells. So as we discussed, using a spot price instead of a top oracle is a sure way to lead to oracle manipulation attacks. And even though, as we saw, the protocol Rodeo Finance was using a time-weighted average price oracle, it was not configured correctly. So if you are using a time-weighted average price oracle, then you must make sure that it's configured correctly and that there is some redundancy built in to this oracle, so that if there is some type of price manipulation, the top oracle can respond accordingly. Also, a code smell to look at is if a Protocol calculates the price of the token using the token supply. This is an incorrect way. You should be using an oracle in this case. Um, improper oracle configurations is also a code smell. One that can be seen currently today is not getting the updated round data from a chain leak feed. So that's one of those configuration type of vulnerabilities that can occur. Also, you should be checking if the oracle is actually using the correct price feed. Some oracles may use improper price feeds. Protocols may not account for the decimals that the oracle returns. So these are some things specifically speaking to oracle configurations. And then lastly, oracle centralization. I touched on this in this first bullet point, but you should have some type of redundancy within your implementation. Don't just trust one oracle. Maybe you should incorporate 2 or 3 oracles and return these prices to your users accordingly based off of what those oracles all are returning, as well as what happens if one of those oracles returns stale data or it's just down, that feed is down. So these are some things you want to think about whenever you're building your protocol, but as an auditor, these are some easy code smells to determine if there's likely some type of oracle manipulation attack. Up next, we have Module 2, which speaks to front running. So we're going to go through what is a front running attack. We're going to walk through a simple front running attack example. Then we're going to look at a hack walkthrough and then describe some front running code smells. All right. So every transaction on blockchain networks undergo a period of visibility and the mempool before execution. This information leak can be leveraged by attackers to influence the course of a transaction's execution. So what this means is every transaction in the mempool is visible by essentially anyone, and anyone can front run other transactions by paying a higher gas price. So we have this example here where Alice submits the correct answer to her quiz game with 15 Gwei. Bob doesn't know the answer, but he's monitoring the mempool and he finds the transaction that Alice submits. Bob submits the exact same transaction with the correct answer, but pays 50 Gwei. Because Bob pays a higher gas fee, Bob's transaction is going to be the one submitted on chain, even though Alice was first. This is a prime example of a front-running attack. Alright, so we're going to take a look at a quick front-running example. The game's premise is simple. A player must guess a particular number that has been hashed and stored within the contract. So if we take a look at this code here, we have a guess the number challenge game. We store the challenge as a bytes 32. Then when the contract is deployed, we have this challenge variable initialized, and that can be any number that the deployer wants to set. Then the users have the ability to guess what this challenge value is, and they have to submit a submission fee with that. So essentially it's going to check if the user's submitted challenge is equal to the actual challenge set by the original deployer, then it will be a success. Perfect. And the player that wins will receive the balance that is set here. This is the balance of the contract. So that's how the game is played. People will submit their guesses, and that will store these tokens, or this ETH, in the contract, and the player that guesses this right will win the game. So that's the premise of this game if you read through the code. Now, let's say I'm Alice, and I actually figure out this challenge. I figure out the number. I submit this number, but Bob basically can see my transaction in the mempool. They can see my number in plain text. They know what I submitted. Bob can just take that, submit this guess with a higher gas price, thus front running me and taking all of the balance of this smart contract. So front running attacks can happen. Won't say that they're very prevalent at the moment, but these are things to kind of look out for when you're reviewing smart contracts. And as developers, you should be thinking about these kinds of things. If you have any type of gambling or casino or game-based smart contract, this is something you're really going to have to look out for. So as GameFi expands, we may see a lot of these attacks actually happening in real time. So you should definitely know this attack method. This is honestly one of those basic attacks that's crossed off as a beginner when you're learning about smart contract vulnerabilities. All right, so we're going to look at a real hack. It's the RADT front running attack mixed with an Oracle manipulation attack. So we're going to take a look at the contract flow, and then we may take a look at a reference for this. All right, so we have a few things here. Essentially, this contract was vulnerable to a front-running attack and then also a price Oracle manipulation. So you can see where you can't really simulate the actual front-running, but this is the transactions that were called that front-ran. I believe the original developers of RADT. So we have the attackers approving the router and then also calling a flash loan to the RADT contract, which allowed them to buy some RAT, transfer it, and then withdraw one of the token pairs or one of the tokens from this token pair, and then sell RAT, which ultimately resulted and them gaining some type of arbitrage because of this Oracle manipulation from this flash loan that resulted in the attacker running off with about 100K worth of funds. So you can take a look through this contract to see this in action. But what's interesting is, let's bring this over here. Originally, there was another caller of this specific transaction, and I believe this is probably the developers of RADT. But what happened was the attacker essentially front ran the original call and performed their own swaps, which resulted in the exploit. So it's pretty interesting that So here's the original attack transaction. Sorry. So let me go back. So I said that the developers were supposed to be calling this original function. Didn't mean to say that. Another attacker was performing this Oracle manipulation attack, and essentially probably a mevbot or someone who's monitoring the mempool picked up on this and actually front ran the attack. So it's kind of interesting that an attacker used a front running attack to essentially beat out the other attacker. Same with the Alice and Bob situation. Alice had the right answer, was going to get some money. Bob came in, front ran the transaction, and performed the submission for the game. Similar case where there was an actual attack. Pick this back. There was an actual attack transaction from someone else, and this was front ran by another person, which allowed this full attack to go through. So you can take a look at this. Very interesting stuff. Very interesting way for this to happen, as we can see right here. So here's the original attack transaction, and then these are the front running transactions. So very, very interesting not use case, but very interesting example where front running was used to essentially exploit an exploiter. But yeah, very interesting case. You should take a look more into this. All right, so now we're going to look into front-running code smells and ways to detect a potential front-running attack. First, you want to minimize the relevance of transaction ordering or timing. If you have a GameFi type of DApp or smart contract, you may want to figure out an architecture to prevent these kinds of cases. Next, you want to implement a two-step transaction scheme. So when you have a two-step transaction scheme, you essentially have two different sets or steps of transactions that you have to submit in order to prevent a front-running attack. So, for example, you may hear a two-step transaction scheme such as two-step claiming. If someone has the ability to claim, let's say, some funds out of a smart contract, they may need to first submit a request to make this claim, and then in the second transaction, they'd have to submit the actual transaction to claim these funds. So that's two steps. Same with updating specific admin privileges. You may see two-step transaction schemes used here. These are just ways to prevent front-running attacks because you need to have a specific person or address make that first transaction in the two-step scheme. Next, you have a commit and reveal scheme. This is also a part of a two-step transaction scheme, but it just uses a different mechanism. So when you commit, you'd essentially submit your answer with that first answer being submitted as a hash, and then sometime later you would reveal your answer with the seed value for that hash. So that's how you can kind of prevent an attacker or someone monitoring the mempool and attempting to submit your answer. Why can't they do that? It's because that has been hashed, and it'd be a little difficult for them to figure out what that answer is in such a short amount of time. Next, you must be aware of be aware that all transactions start on the mempool. That's just something you should honestly have wired in your brain as you're building DeFi protocols and as you're auditing smart contracts. And then lastly is Flashbots. Flashbots also offers various services for various Mevbot types of activities. So you can use Flashbots to perform certain front-running attacks, but also you can use them to prevent these front-running attacks. All right, so in this last module, we're going to go through signature-related attacks. I know we also mentioned signature malleability. This is going to pretty much be lumped in together. So we're going to do a high-level overview of signature-based attacks. We're going to walk you through a simple example, then perform or show you the performance of a real-world hack. Then we're lastly going to round off with walking through some code smells for signature-based attacks. All right, so high-level overview for signature-based attacks is a signature implementation in a smart contract can be incorrect. Implementations can allow modifications or incorrect use of a signature without a private key. And this is bad news. If, for instance, someone can authorize themselves as another person using a signature because the implementation is incorrect, we have essentially just messed up the purpose of using blockchains and using our signatures in smart contracts. The whole idea of a private key is so that when you sign a transaction, you are authorizing that you are who you say you are. And if there is an implementation within a smart contract that allows other people to pass themselves off as another person, this is where these attacks can arise. All right, so in this example, EC Recover is used, and the developers failed to understand, or at least they failed to check what EC Recover returned. EC Recover returns a 0 or the address recovered if successful. So 0 if false, and then the address that's attempting to be recovered if successful. So in this attack, an attacker was able to force a zero comparison, causing a signature check bypass, which allowed them to essentially pass off as an authorized signature. So let's take a look at this. We have this valid order hash function, and we have basically you submit a hash order and the signature components. And what this does is it takes recover, which uses EC recover to take the signature and validate if it is a valid signature or not. So in this case, a user is able to manipulate this valid order hash by passing in an incorrect signature, and that makes it essentially return 0. And what this does is it doesn't check if 0 is being compared to 0, and that's where that's where the mistake lies in this code. So o.maker, essentially someone can pass in the 0, can pass in 0 for this o.maker variable, and then pass in an incorrect signature, which then calls EC recover. Once it's invalid, this also returns 0. So this is going to look like require 0 == 0, which is going to be true, and that is going to, from the smart contracts sense, pass it as a valid signature, even though it was not. So you might need some time to take a look at this attack. Shout out to Dev Dacian for pointing this out in one of his articles. But this is a very common attack that can happen when using signatures or EC recover. All right, so now we're going to take a look at a real-world example of the Azuki DAO exploit. If you aren't familiar, Azuki is a famous NFT that had a lot of notoriety last year in 2022. So just to show you, this is what not Suzuki. This is Azuki. You may be familiar with these PFPs if you've seen them. But yeah, pretty cool art, but not so great. Smart contract design. I actually won't say that. Smart contract design was great, but if you miss one thing, the attacker can exploit it and cause some huge issues. So, not throwing any shade to the Azuki DAO development team, would have done a much better job than I definitely would have. But there was a signature issue with their smart contract. So, for instance, within this contract, it allowed users to be able to mint an Azuki or an NFT. Oh, actually, I don't know if this is for the actual Azuki, but the Azuki DAO contract, and there was a minting feature for this contract, or a claiming feature for this contract, and essentially for the claim function. For the claim function call, a user had to submit their signature. But what this didn't check is that the signature they didn't check for the signature to be replayed. So essentially what someone did was called the claim 200 times with the same signature. And this allowed the user to claim these 200 times. So when you have a contract that allows people to submit signatures to maybe mint NFT or claim some sort of tokens or DAO tokens, whatever it is, there needs to be some type of check to make sure that same individual cannot submit their signature again. So this is what happened. Maybe we can take a look at let's take a look at a Twitter thread if there is one, so you can know to look this up as well. Here's one. Okay, so it has the whole attack process, and now we already walked through it. But if you want to take a look, then take a look at this Shark Team analysis of the Azuki DAO exploit. So that's a real world example where a signature type of attack was used and it allowed someone to exploit a protocol. All right, so let's take a look at some signature attack code smells and things you as developers and auditors can use when building or reviewing smart contracts. So failure to check for signature replay and reuse. This is a common attack that's performed with signatures. Developers may understand and implement signature types of checks from a very high level or just like a surface level understanding. But if you don't understand what signatures really are, this can lead to these types of attacks. So if you're reviewing some code and you see that they use signatures, they use EC recover or some type of signature function, check and see if you could reuse the same signature once. These are some things that are not checked. Next is taking a look at the nonce of a signature. Some signatures may not check for a nonce. This can also lead to signature replay attacks, but this is just a good parameter to check for when incorporating various signature functions. And again, if you're not familiar with nonce, go take a look into that. A nonce is usually the number of times your wallet has essentially performed a transaction. So if my wallet has not performed any transactions, it'd have a nonce of 0. If I performed 1, it'd have a nonce of 1. So, you know, if I have performed a transaction with nonce 2, but a certain signature function doesn't account for my nonce, someone may be able to resubmit my signature of that nonce 2, not even understanding that that this nonce shouldn't be replayed. Next is improper use of signature-based functions. Specifically, what we want to get at here is signature functions require various parameters to be used in that function. And if you don't use these parameters correctly, or you are mistaken of the return values of these functions, this can cause a signature type of attack. And we've already showed you the one with EC recover. Is some developers automatically think that EC recover either it returns the address, or it may revert, or just return a failure of some sort, but it returns 0. And so when developers don't check for the 0 return use or case or path within their smart contracts, this can lead to some type of signature based attack. And then also another important one is checking for lack of cross-chain signature checks. So if I had a signature that's on Ethereum, it may it would need to have whenever we're working with another chain, another chain, let's say it's an L2 like ZK Sync, there needs to be a signature check to also validate for the chain ID. It needs to make sure that we're on the proper chain ID when validating that signature. So chain ID is also another important parameter, but this is just something to include in your signature checks if you're dealing with bridge contracts or anything that relies on signatures being used on an alternate chain. All right. All right, in this last module, we're going to go through denial of service attacks. We're going to run through what is a denial of service, give a simple DOS example, or denial of service, DOS for short, do a real world hack walkthrough, and then talk about some code smells.
Now we're going to go through an example of what a denial of service attack may look like. What we're looking at now is a contract called Oxygen with a single function called bid, where this function is essentially keeping track of the highest bidder, and the name of that, the address of that bidder, they label as front runner. This has nothing to do with front running. This is just the address whoever has the highest bid. And so what this function does is it checks that the amount of ETH sent is higher than the current highest bid. If it's not, then this transaction reverts. But if it is, this contract will refund the previous highest bidder and then update the values front runner and highest bid. Now, I want you to take a few moments, pause the video, and see if you can identify the denial of service vulnerability here. Okay. So if you notice here, when the bid method is trying to refund the previous highest bidder, this transaction will revert if it fails to send that ether, meaning whoever tries to bid higher than the previous highest bidder won't be able to submit their bid if the previous highest bidder can't be refunded. So this text just says what I was going through in words, but I just want to reiterate this bid, the denial of service vulnerability here is the bid only functions if it can refund the previous highest bidder. So what an attacker can do is create a contract that submits a highest bid here, and that contract can implement a fallback or receive method that automatically reverts. And what that will have the effect of is this bid contract won't be able to refund that malicious contract, meaning they will be able to win the bid unfairly. A really great resource if you want to learn more about denial of service attacks is this blog post by an auditing firm named Quill Audits. So it's titled Denial of Service Attacks on Smart Contracts, How to Fix and Avoid Them. And we're just going to look at the table of index here, and it talks about some of the things we've talked about where, denial of service by taking advantage of gas limit or gas limit of a specific contract operation. But they go into a lot more depth and give a lot of other examples as well. So I highly recommend going through this resource if you're curious to learn more, or if you're in an audit and you're wondering what are some ideas on how you can break this contract. Now I want to go through a real world example of a denial of service attack vector found in the wild. So we're again looking at the DeFi Hack Labs, which has a proof of concept. But what I want to pay attention to is this blocksec breakdown, because I think they do a very good job of making it more concise. So what we're looking at here is a method called process refunds. If you remember from the previous example we just talked about, where we were able to break the contract's functionality by preventing refunds, this attack vector is very similar. So there's a function called process refunds. This is inside of an auction. And notice that what is going on is there's a for loop going across multiple bids in an auction, meaning that this process refund is doing a bulk transaction to try and process multiple refunds in a single transaction. And they have this require statement here that is requiring for every bid in this loop that they're trying to refund, it has to be successful or the entire transaction reverts, meaning even if there was 100 bids that were successfully refunded, if that 101st bid fails, all 101 of them fail, breaking this contract's functionality. So this is an example of what a real world denial of service vulnerability looks like. Now, when you're writing code or reviewing code, what are some code smells that may indicate a denial of service attack vector? Firstly, operations with unbounded arrays, like in the Anchor Finance example, where we saw iteration over a unbounded array of bids. There's also gas denial of service vulnerabilities if you know there's an array with tens of thousands of addresses to try and loop over where it just reaches the block limit. So those are some things to look out for. Another concept that brings a little bit of DeFi element in is called dusting. So dusting is when someone sends the smallest possible amount of ETH, like one way possibly, in order to break a contract functionality in some way. One way I've seen this is in a lending and borrowing protocol, where if someone has borrowed debt that becomes bad debt and should be able to be liquidated, I've seen a denial of service vulnerability where an attacker could front run a liquidation transaction. So if someone was trying to liquidate that attacker's bad debt, they would front run it and open a new position with one way, so that whenever that liquidation tried to run, it would revert because there was still an open order. So that is an example of something called dusting, where someone is using a very small amount of a token or native ETH to deny some functionality of a contract. Thirdly, like we talked about before, being aware of gas limits in a transaction and also a block's gas limit. And lastly, being aware that sometimes it makes sense to restrict addresses to externally owned accounts, so that contracts can't interact or send ETH, but being aware that there are some wallets, like multi-sig wallets and account abstracted wallets, that are implemented as smart contracts. So that's the trade-off if something is restricted to EOAs, is that might break multi-sig wallets on your contracts.